In this example, let's just remind you, there's a block A that has a mass m equals 8 kilograms, and with the initial speed v1 equals 15 meters per second. And this is a rough surface, so the friction coefficient equals 0.15. And there's a force that's pushing this block A, and the duration of how long that force is applied to block delta t equals 0.2 seconds. So we're trying to find what's the speed of block A at t equals delta t, and that's part A. And for part B, what's the speed of block A when t equals 2 times delta t? So as you may notice the difference from 4B and 4C. In 4B, what we're dealing with is looking at the speed of kinetic energy or potential energy at two different locations, at two different positions, right? However, in section 4C, we're looking at the different speed at different time points. So that's the major difference here. So in order to solve this problem, let's first draw the free body diagram and set up our coordinate system. So we only have one mass, which is A, and if we draw our free body diagrams, we have the normal force, weight force, friction force, as well as this force that is pushing this block A. And we can set up our coordinate system as I and J. And the step 3 is we want to look at all the forces and write them in the vector form. So let's just do that, and we were going to have force that is on I direction, positive I, have friction force, it's negative I direction. And we know friction force equals mu n, and this normal force, and in this case, normal force equals to the weight force. So we can keep writing this as mu mg I. Normal force equals n on j direction, and weight force is negative mg on j direction. And if you look at all the forces, you will realize that the sum of forces on j direction equals to 0 in this case, right? And the sum of the forces on I direction does not equal to 0. So the first one, sum of the forces equal to 0, that led to the conservation of momentum. And this doesn't equal to 0 would not lead to that conclusion, conservation of momentum. So keep that in mind. Because this block is only moving on I direction, so I direction is what we care, and that can tell us more information. So we're gonna apply the linear impulse momentum equation on I direction. Step 4, apply linear momentum equation on I direction. And by using sum of all the forces on I direction we have F minus that's friction force F plus, and that is dt equals m v2 minus v1. And we can write those forces in terms of I and J's, in this case I. This is I direction linear momentum equation. And that is the integral start. If we're trying to solve part A, and part A, we want to find the t equals delta t. So the range of integration should be from 0 to delta t. And F equals Fi plus the friction force is negative mu mg I dt. On the other hand of equation, just m v2 minus v1. Okay, and how do you solve this? We can, because we have plus sign instead of the integral, we can break it down, right? So this can be written as integral 0 to delta t, just for the first term, fi dt, plus 0 to delta t, negative mu mg I dt, that equals m v2 minus v1. Okay, so now we have two integrals here. How to solve this? If you look at f, let's consider a variable within this range 0 to delta t. Let's go back to the profile of f, and you will realize between time equals 0 to delta t, f is a constant, right? That's a constant. So the integral of that simply means the area under that curve, under that constant line. So this will give you a rectangular shape. The area of that area is f0 times delta t. So here we can write this as f o delta t. That's the area under that curve. Plus the second integral here is for the friction force. Friction force is a constant force during the whole 0 to delta t. Therefore, it's simply just negative mu mg delta t equals m v2 minus v1. And here, the unknown is v2. We're trying to find this v2. So you can throw the m and v1 to the other side of the equation and to get expression for v2. And you can write v2. So v2 can be written as delta t m f o minus mu mg plus v1, and this is on the I direction. So there you go. That's how you find the velocity for block at time equals delta t. This is the expression. If the numerical value is given, you were able to find a value for v2. So any questions? So that will tell us how to solve this first part. Any questions, guys? Okay. If you don't have any questions, then we'll look at part B. Part B is when you find out velocity of block A at t equals 2 delta t. So the only difference is at part A, we're looking at t equals delta t, but part B is t equals 2 times delta t. So B, and the only modification we would do here is to change the range of integral from 0 to 2 times delta t. And fi plus negative mu mg I dt equals m v2 minus v1. Is that right? So the only thing changed there is this 2 delta t here. Okay, and we can do the same thing. We can break this integral to two parts. The first part is 0 to 2 delta t for f dt, and plus 0 to delta t for the negative mu mg I dt equals m v2 minus v1. Okay, so now we have this two integral here. So my first question is, what's the result of this integral here? I'm going to call someone to tell me what's the result of this integral. And Jack, can you tell me what's the result of that integral?
Negative mu times mass times gravity times 2 delta t.
Yeah, since mu mg, the friction is constant during the whole duration. So that it's simply just the force times the duration of time. So let's write that down. That's, oops, negative mu mg 2 times delta t, right? Okay, next, Dalen H here. Can you tell me what's the result from the first integral here?
It'd be the area under the curve, but you'd have to add the little triangle bit. So it'd be f0 times delta t plus your 1/2 f0 2 delta t.
Yes.
Or yeah, it'd be another delta t. Yeah, it wouldn't be 2 delta t.
Yes, that's right. So the integral for the first part is going to be just the total area under this curve from 0 to 2 delta t, right? If you look at the shadowed area, it's just a right triangle here plus a rectangular, right? So let's write that down. This first part equals to f o delta t plus, that's the area of that rectangle, plus the second part is the small triangle, which is f o times delta t over 2, right? So this whole thing equals m v2 minus v1. Then can do the same thing. Just write v2 at one side of the equation, and throw everything else to the other side of the equation, and we will end up with, so f delta t plus f delta t over 2, that will give you 3 over 2 times f delta t, right? 3 over 2 f delta t. And you have minus 2 delta t mu mg plus, oops, plus v1, and this goes in times 1 over m. So that will give you expression for v2 when t equals 2 times delta t. All right, any questions? So that's how we solve the both a and b.
Would it matter if you do times 1 over m, or can you just do it all over m?
Doesn't matter. You can do this 1 over m instead of this bracket. But here I do find the mistake I made. So don't forget, we have a vector here, so you need to have a vector, unit vector. Make sure your result is consistent. Okay. Any other questions, guys? Now, let's take a look at another example, which is force state 3. It's an example on your textbook. Okay. So in this example, force state 3, and we have two boats. We have a tug and we have a barge. So at the beginning, they both are moving at the same speed, VA1. And at one moment, the engine of the tug is shut off, and there's a wrench on the tug start to pull this barge close to the tug at the speed of VB/A. And we want to find out what is the velocity of the tug once the engine's shut off, after engine is shut off. And the second part we're trying to find is what's the average tension in the cable between these two boats. Okay, so this is set up the problem of force state 3.
Are we assuming that there's no friction from the water?
Yes, that's a we call it. There's no friction, no resistance from the water. So there's no mu term. Okay, so in order to solve this problem, first we need to look at these two boats, those two boats as a system, as a whole system. Then if we look at them as a whole system, and when we do the free body diagram, we do not need to care about the internal forces. So when you have free body diagram for A and B, and there's no tension force between them. We only have wave force for A, normal force for A, wave force for B, normal force for B. And there's no tension force because we look at them as a whole system. And since the boats are moving to the left, so I would set up my coordinate system, I and J, in this way. So my I would line up with the motion of the boat. And I have a question for you. What's the sum of forces on I direction? Isaac, can you tell me what's the sum of forces on I direction?
Wouldn't it just be T?
Do we have
There's-
T in our free body diagram?
No. So in that case, it would just be 0 since there's no forces acting on the X direction or the I direction.
Yes, correct. So there's no forces. Sum of the forces equal to 0 on I direction. And hey, Chase, can you tell me what's the sum of the forces on J direction?
0.
Yeah, 0 as well. So both sum of the forces on I and J goes to 0. And so from the introduction of this section, we mentioned if the sum of forces equals to 0 at a direction, that tells us there's a conservation of momentum on that direction. So in this case, we have conservation of momentum on both I and J directions. Now we can start to apply the linear impulse momentum equation. And here, because both boats are moving on I direction, J direction doesn't tell us anything. So what we care about is the linear momentum equation on I direction. So first, the linear momentum equation on left-hand side, that's your linear impulse. On the right-hand side of the equation, that's the change of momentum. Since here we have two masses, MA and MB. So when you calculate the change of momentum, you need to consider the sum of both masses. And because we know the sum of the forces on I direction equals to 0, so we can simplify our impulse momentum equation to 0 equals ma va2 plus mb vb2 minus ma plus ma va1 plus mb vb1. Okay, so here va2 and vb2 are the speed of both A and both B after engine is shut off. And VA1, VB1 are the speed of both before the engine is shutting off. And because in this given condition, we know both boat, the tug and the barge are moving at the same speed, VA1 at t equals 1. So VA1 equals VB1 equals this VA1I. They are both moving on I direction. Another given condition we know it's this wrench has this speed at VB/A. So the wrench on the tug is pulling this barge close to the tug, right? At this speed. And what we learned from the first 3 chapters is this is a relative speed. VB/A can be written as VB minus VA, right? So that's how we can get this first 3 equations. And if you look at this equation 3, we have VB/AI equals this VB2 minus VA2. We can also kind of change this a little bit to find the expression for VB2. We'll use that later. VB2 can be written as VA2I plus VB/AI, right? Okay. Now we have these 3 equations, and we can plug both 2 and 3 into 1. And so equation 2 tells us this VA1, VB2 are the same, so we can both replace them with VA1. And we also can use the equation 3 to substitute VB2 in equation 1. So VB2 is here. We can substitute this term with VA2 and VB/A. So once we do that, we end up with a little bit longer expression with VA2, VB2, VA1, VA1 inside of the equation. And by substitute that VB2, let me increase this. Okay. By substituting VB2, we can further simplify this to 0 equals MAVA2I plus B VA2I plus B VB/AI minus A VA1I parenthesis plus B VA1I. Okay, so now you realize the unknown V2 has 2 terms here, V2, V2. And the rest of the variables like VB/A are given. VA1 is given, VA1 is given. So we can pull this VA2 out, right? To find the expression for VA2. So if you do some arrangement, you will get VA2 equals to negative over A plus B. B times VB slash A plus VA1. It's on I direction. This is expression for VA2. Okay, any questions? Any questions on how we find out expression for VA2, which is something we're trying to find here? Part A, we need to find VA2. That's the speed of the tugboat after the engine is shut down and the wrench is running at a certain speed. Okay, then we can look at the second part of this problem. We need to find out what's the average tension on the cable. So we have a question for, let's see who's here, Jack. Can you tell me, are we able to find the tension force by using this free body diagram? This free body diagram is for the whole system.
We could if we had the tension between the rope.
So, the tension is not exposed in this free body diagram. So that's a problem of taking the whole system for free body diagram. If you have the free body diagram for the whole system, you cannot lost all the information inside of the system. We call it internal forces. So in order to solve for the tension force in the cable, and you need to only take one mass to analyze in order to expose that tension force. So for part 2, what we need to do is we need to only look at one boat. In this case, we can look at boat A, that's a tugboat. Then we can just draw the free body diagram only for this tugboat. And keep the coordinate system INJ. For this mass A, we have weight force. We have normal force. And now, since we're only looking at this boat A, this boat is pulling by the rope T here. So now we have tension force in our free body diagram so that we can apply equations to solve this problem. Okay. In which direction this tension force is on? Zach, which direction this tension force is on?
I would sit on the negative I direction.
Yes, negative I direction. So I direction, it's a direction we care about. J direction doesn't really tell us much. So we can apply the impulse momentum equation only for the I direction. Apply the linear impulse momentum function. Sum of the forces dt equals mv2 minus v1. That's a linear momentum, linear impulse momentum equation. In this case, the sum of the forces on I direction would be just t, right? We only have t. And here m is ma. and VA2 minus VA1. Okay, and this problem is asking you to find the average tension force. So if we're only looking at the average force, and we can think that force is constant during the whole duration, delta T, and then we can just take that out as T average times delta T. That's from the left hand of the equation. That will give us MA. Can write VA2 VA2I plus VA1I. Okay. This tension, it's a vector and it's on I direction. Oops, it's on negative I direction. Okay. So one thing to be careful is in section C and the linear impulse momentum equation, it's a vector equation. So everything, all the forces, velocities are in forms of a vector. So you need to make sure everything's in terms of ij. Yeah. So we can write this average tension force in the cable as something I direction, since we know it's on the negative I direction. So that is negative T average, that is I. And we can throw this delta T to the other side of the equation, and we end up with MA delta T VA 2 plus VA1 I. Add a bracket here. Okay. So now, if you look at the expression here, VA1 is given. Yeah, that's given in this problem. And VA2, it's what we solved in part A, right? Let's go back to part A. Yes, this is expression for VA2. And if we can actually plug in VA2 in this expression, then we're able to find out T. Can write T average as the vector. Can be written as A over delta T times B times A plus B VB slash A. Negative on I direction. There you go. That's how we find out the average tension in the cable by using the linear impulse momentum equation. And just be careful when you write the result. Make sure you have vectors and vectors on both sides of the equation. Okay, any questions, guys?
How did that velocity A1 and the vector at T average times delta T equals MA VA2 I hat plus VA1, how did that become positive?
Oh, let's double check here. V2 minus V1, and here VA2 minus VA1, and down here, you're right. I think here's this should be negative, right? Now it should be right, Chase?
Yeah, now that looks right.
Yes, so in this section, I think the signs are very the troublemakers. So make sure once you set up your coordinate system INJs, and both your forces and the velocity should be consistent with the coordinate system you set up. For example, here we set up our I as pointing to the left as a positive direction. So when we did our tension force T here, the tension is on the negative side of I. So I will add a negative sign to that to show that's on the negative direction. Also, the result we get here also has a negative sign for the tension in the cable. Okay. Right now, we did 2 examples in force C1, force C3.